Hello, my name is Xixiang Du, and this is the presentation of my project for pattern classification class. My project is face recognition using eigenfaces. The main purpose of this project is to develop a system that is able to recognize a person's face by comparing facial characteristics to characteristics of the known person. There are two main parts of this project. The first part is generating the eigenface spaces, and the second part is recognition. Now let's start with the first part. In the first part, we first introduce eigenfaces and PCA, which means principal component analysis. In general, PCA is a statistical procedure that uses an orthogonal transformation to convert a set of observations of possibly correlated variables into a set of linear uncorrelated variables. The reason why PCA is suitable for face recognition is that face images are always similar to each other and clearly share the same general pattern and structure. Now let's see how PCA works for face recognition in details. A n by n pixel image of a face is represented as a vector occupy a single point in n-squared dimension image space. Image of faces being similar in overall configuration will not be randomly distributed in the huge image space. Therefore, they can be described in a low-dimensional space. Main idea of PCA for faces is to find vectors that best account for variation of face image in entire image space. These vectors are called eigenvectors. Construct a face space and project the image into the face space. Now let's talk about eigenspace and eigenfaces. Face images are projected into a feature space called face space that best encodes the variation among known face images. The face space is defined by eigenfaces, which are the eigenvector of the set of faces. Now let's see how to calculate eigenfaces. First, we have to calculate the average face, and then collect difference between training image and average face in matrix A, which is m by n, where m is the number of pixels and n is the number of images. The third step is to calculate the eigenvector of the covariance matrix C, which is m by m, to given eigenfaces. Because m is really big, so this process would be time consuming. But there's one way to solve this problem. If the number of data points is smaller than the dimension, which means n is smaller than m, then there will be only n minus 1 meaningful eigenvectors. Instead of directly calculating the eigenvector of C, we can calculate the eigenvalues and the corresponding eigenvectors of a such smaller matrix L, which is n by n. This is what PCA contributed to face recognition. It greatly reduced the computation time. If lambda I are the eigenvector of L, and then A lambda is the eigenvectors for C. The eigenvectors are in descent order of the corresponding eigenvalues. Representation of face images using eigenfaces. The training face image and new face image can be represented as linear combination of the eigenfaces. For example, when we have a face image U, since the eigenvectors are orthogonal, the U can be described as the sum of AI product phi I. So the AI can be described as this. This is example of the eigenfaces. This is the figure of training images. Next, let's talk about averaging technique. Within a given database, all weight vectors of a like person are averaged together. This created a face class where an even smaller weight matrix represented the general face of the entire system. This technique also reduced the computation time. And this is the example of the average image. Now let's talk about how to projection how to project the image into the face space. A face image can be projected into this face space by this formula here. Here k can be 1 to m. When k equals to 1, we get the dimension 1. When k equals 2, we get the dimension 2. Finally, we can get a vector p, which is the projection of the image into the face space. Now let's talk about the recognition part. The test image is first the test image is projected into the face space to obtain a vector p, like just talked before. And the distance of P to each face class is defined by D. And D is described like this. A distance threshold theta c, usually defined as half of the largest distance between any two faces images, can be calculated like this. Next, we need to find the distance between the original image X and its reconstructed image from the eigenface space XF. The D square is equals to X minus XF square, where XF is this, yeah. Here the phi is averaging face, and this is the projection of the test image. And then we can do the recognition. If D is greater than or equal to theta c, we know that the input image is not a face image at all. And if D is smaller than theta c and dk equals to the minimum of dk is smaller than theta c, then the input image contains the face of individual k. That means this image is in the database. And if D is smaller than theta c and dk may be greater or equal to theta c for all k, then the input image contains an unknown face. That means this face image is not in the database, but it's actually a face image. Here are the results of the test. Here we can see the left side is the test image or the given image, and the right side is the image that the system found from the database. Here we can see it's the same person. And example 2, we can see it's again the same person. Example 3, the same guy. So the test is successful. This system successfully choose the right image from the database, matches with the test image. Here's the conclusion. This face recognition project uses eigenface recognition with averaging provide a high accuracy system to do face recognition. Further research could be conducted into a viability of using eigenfaces and weightings taken for varying angles and lighting situation in order to allow for greater variability in both image and detection opportunity. Clearly, the eigenface offers much promise for the field of facial image recognition, but not before some technical refinement. The last part, let's talk about the limitation of the eigenface approach. First, is the variation in lighting conditions. Bright light causing image starvation. And the second part is the 2D feature distance appears to distort the performance of this system. And the third is the expression. Change in feature location and shapes will harm the performance of the face recognition using eigenfaces. Alright, this is the presentation part for my project. Thank you for listening. Thank you very much.